This is review video 29. What is a relative rate expression? So to sum up, we've talked about potential energy of reactions. We've talked about kinetics and what we're going to study when we look at how fast reactions go. But to really study the rate of reactions, we have to have an actual numerical rate. So we have to express that numerically to be able to study it correctly. And a relative rate expression is going to define numerically how quickly reactants disappear and products appear individually within a reaction. Specifically, the relative rate of reactants and products is going to be defined in terms of the slowest chemical to react or be produced. So if I'm looking at this little reaction right here, we have 2H2 plus O2 yielding 2H2O. The slowest chemical to react is going to be O2, and I know that because it has the lowest molar coefficient. And that means that the entire rate of reaction is going to be defined in terms of that one, and every other reactant and product is going to be defined in terms of that one. In terms of writing the actual relative rate expression, rate is equal to the change in concentration of a reactant or product, so it could be any reactant, any product, whichever one you happen to be looking at, divided by the molar coefficient N. And in case you were curious, the molar coefficient for hydrogen is 2, for oxygen it's 1, and for water it's 2 in that reaction. And then also on the bottom is our change in time. Now we abbreviate it to look like this. So we have the brackets. The brackets mean concentration, right? And so we're going to have a change in concentration overall, so delta A, divided by the molar coefficient N times the change in time. So again, if you forgot, that triangle delta means change. So if you ever see that, it means change of something. Now, reactants are always going to have a negative rate because they are going to disappear if the reaction is moving forward. Products are always going to have a positive rate because they are appearing as that reaction moves forward. And generally speaking, we define reaction rate in terms of the forward reaction. Another way you can look at it besides that fraction thing that I just showed you is you can look at it graphically as well, which might be easier for some of you to follow. So if we're looking at this reaction down here, we have 2NO plus O2 yields 2NO2. So our two reactants, the blue one is oxygen, and that one has a negative slope, again, because that is disappearing. The green one, NO, has a negative slope because it is disappearing, it's a reactant, and the red one, the product, NO2, has a positive slope because it is appearing. But there's a couple of things that I want you to note here. The first is that NO and NO2 on that graph, they have mirrored slopes. So for as quickly as our NO2 is disappearing, for how quickly our NO is disappearing, our NO2 is appearing at the same rate, which makes sense because their molar coefficients are the same. Oxygen, on the other hand, has a slope that is about half as steep as your NO is, because since its molar coefficient is that little invisible 1, it means it's disappearing half as fast as the NO happens to be disappearing. So you can see that represented graphically. But you're not always going to have a graph to look at, so you need to be able to take the chemical reaction and write a relative rate expression for the reaction anyway. So we're going to practice doing that. We have this reaction up here to look at, and we're going to write a relative rate expression for every single reactant and every single product that is in that reaction. All right? So we know that rate is equal to the change in concentration of a reactant or product divided by our molar coefficient times the change in time. And this problem did not give us any other information besides the reaction and saying, hey, write a relative rate expression. So you can't plug in numbers that you don't have. So instead of trying to figure out numbers, you're just going to take what you have. This first reactant, NO, I'm going to say, okay, that's a reactant, so I know that its relative rate expression is going to be negative. Then I'm going to put the change in concentration, so that delta means change, and we're going to open a bracket and we're going to write NO, because that's all the information we have. We're going to divide that by its molar coefficient, 2, times change in time, so delta T. And that's its relative rate expression. We don't have any other information. We don't know how much it's changing in concentration. We don't know how much time has passed, so this is all we can do. We're going to set that equal to the relative rate expression of oxygen. So we're going to do this one next. Again, it's a reactant, so it's going to be negative. We know that oxygen is going to change in some way, so we have delta and we put oxygen. And its molar coefficient is 1, so we don't need to write that down there because 1s are implied, and so we can just put delta T on the bottom. We're going to set that one equal to our product. Since it's a product, we know that its relative rate should be positive because it's appearing. Then we know it's going to change in concentration over time, so we're going to put delta, open a bracket, and write NO2. We're going to divide by the molar coefficient, 2, times the change in time. That is a relative rate expression. That's all you need to do. The only time you would have to do something else other than that would be if you have other numbers, which in this problem we don't. All right? Now, this problem, on the other hand, we do in fact have other numbers. This problem says, if the rate of disappearance of hydrogen is negative 4.5 times 10 to the negative third molarity per second, what are the relative rates of change of the other chemical species in the reaction? And the reaction is given up here. So let's just take a second. We have one number. We know how fast hydrogen is disappearing. So based on the molar coefficients, I know that oxygen should be disappearing half as fast, and this thing should be appearing at the same rate that hydrogen is disappearing. That's what I know based on looking at it. However, this doesn't say take a guess. It says what are the relative rates of change. So if we're going to calculate this, we have to actually start by writing a relative rate expression. So I'm just going to do that based on this equation. I'm going to copy the equation down so I don't have to keep scrolling up and down. All right. So step 1, write a relative rate expression. Cool. Rate equals, these two are going to be negative. So I have negative delta H2 over 2 delta T equals negative delta O2 divided by delta T, because again, the molar coefficient is 1, is equal to positive delta H2O divided by 2 delta T. Now, you have this relative rate expression, and I'm going to venture a guess that that looks a little complicated. And if you're going to be doing math, we want to simplify a little bit. So I'm going to show you how to simplify this to make your math a little bit easier. What we're going to rewrite this as is we're going to pull out some fractions, and we're going to replace all the deltas and the brackets and everything with the word rate. Okay? So we know that negative 1/2 of the rate of H2 is equal to negative rate O2 is equal to positive 1/2 rate of H2O. All right, so this makes it a little bit simpler to look at, in my opinion. If you want to use this one up here, you go for it, But I like to use a relative rate expression that looks a little bit simpler, so I'm just going to use this one going forward. All right, so what do we have to do? We have to go up here and we have to take the number that we are given, negative 4.5 times 10 to the negative third molarity per second. That is the disappearance of H2, so I'm literally going to plug in that number for the rate of H2, and I'm going to use it to solve for the rate of O2 and the rate of H2O. So let's do that. All right, we have negative 1/2 times that number, negative 4.5 times 10 to the negative third molarity per second, and that is equal to this entire thing, so negative rate of O2. What we have to do to solve is just get rate of O2 by itself, because that's the thing that we're solving for. And so we're going to do that by dividing both sides by -1. Why am I doing that? Because I have to get rid of that negative specifically. And by dividing by -1, that negative goes away, leaving me with rate of O2 on one side. And I just have to solve out the rest of this math on the left. So if I divide by -1 on the left, the negative goes away, and I'm left with 1/2 times negative 4.5 times 10 to the negative third. All right, so I plug that into a calculator and I get negative 2.25 times 10 to the negative third molarity per second is equal to the rate of O2. Now, please recall, sig figs are always a thing, so instead of leaving this as negative 2.25, I'm going to round it to negative 2.3 times 10 to the negative third molarity per second and set that equal to the rate of O2. And that is my first answer. All right? Second answer, we have to go back up here to my relative rate expression because I've done this one. This one's fine. But I still have to solve for the rate of H2O. So I'm going to start with my original number that I was given and use it to solve for the rate of H2O. So once again, I have negative 1/2 times the original number, which was negative 4.5 times 10 to the negative third molarity per second. And that is going to be equal to positive 1/2 rate of H2O from my relative rate expression. And again, what I want to do is solve for the rate of H2O, so I have to get it by itself. And I'm going to divide both sides by positive 1/2. All right, that 1/2 goes away, leaving me with rate of H2O on one side. The 1/2s are going to cancel, but the negative doesn't. So what I'm left with is negative times negative 4.5 times 10 to the negative third on that side. Negative times a negative is a positive, so I am left with positive 4.5 times 10 to the negative third molarity per second, and that is equal to the rate of H2O appearance. Here's my second answer. Now, if you have any issues doing this math, understanding how to set it up, please talk to me because you are going to have to do this in practices going forward.